I want to make sure everyone talks about them the same way that I'm going to talk about them. But so what's going to happen in this class is, in order to simplify or maybe just reinterpret kind of cosine sine type manipulations, we are going to see complex valued functions of time. But notice the dependence is not on a complex variable, but it's on a real variable. So complex valued functions of a real variable. We might also see complex valued functions of frequency, but again, frequency is just a real variable. So, if you look in the course catalog, right, there's Math 185, which is complex variables. Now that's totally different. It involves complex numbers, but it mostly involves functions of a complex variable. So this involves, complex valued functions of complex variables. That's where the nuances come in when you allow your argument to be a complex variable, and then you talk about derivatives of that and what that means. And that's why there's a whole course on complex variables that has a long prerequisite chain. We're never going to do this. We're never in this class going to have a complex variable. Our variables are just real, so therefore it ends up just being simple arithmetic, with real parts and imaginary parts and separating things out. That said, I want to take 10 minutes and fly through my slides just so I've done that, and then I don't have to, every time you come for a question, officers, I don't have to ask you, did you look at the slides and so on. All right? So, but this is what we're doing is very easy, and it's just to simplify cosine and sine manipulations. Okay? There's more sophisticated, there's more nuanced things, and that's why complex variables is a topic of mathematical interest beyond simple stuff. Okay, so these are posted, and I am going to really go fast. It's 10 slides. I don't want to waste. Waste is the wrong word, but I don't want to spend a lot of time on it. So, right, a complex number is really just an ordered pair of two real numbers, right? The real part and the imaginary part. So at this point on this slide, I'm going to write a complex number as an ordered pair of two real numbers. Two complex numbers are equal if the first, these are equal if that equals that and that equals that. The real part equals the real part, and imaginary part equals the imaginary part. You can add complex numbers, you just add their two components. You multiply complex numbers. You can think of it as just this crazy rule with real number multiplication, real number addition, real number subtraction. But we know what that really is doing, is it's doing this, involving this notion of the square root of minus 1. Now if you check, both these rules are associative and commutative, and the distributive law works. It's easy to just verify that using those facts for real numbers, that you know that they are valid for real numbers. By definition, the negative of a complex number, you just negate the real part and the imaginary part. Right? The number 0, 0 is the additive identity, because if I add 0, 0 to something, I'm going to get back the same thing I started with. So this is the 0 that we're familiar with in the real numbers. This is the notion of 0 as a complex number. And 1, 0 is the multiplicative identity. If I multiply alpha beta times 1, 0, I'm going to get alpha times 1 minus beta times 0. That's still going to give me alpha. And then I'm going to get alpha times 0 plus beta times 1. I'm still going to get back beta. So 1, 0 is the multiplicative identity. And it's also easy to verify that if you're not at the 0, 0 point, so both 0, then this number, which is well defined because the denominator is not 0, clearly, because they're not both 0, then this number is the inverse of that number. If I multiply these, I actually get the multiplicative identity. So that's why it's called the reciprocal. It is the number that if you multiply by it, you get the multiplicative identity. So that's the basic, the first order arithmetic of complex numbers, right? So for any real numbers, g and h, if I make the complex number g0 and h0, if I add them, I get g plus h0. And if I multiply them on the previous pages, I get gh0. So it makes sense to think of the real numbers as a subset of the complex numbers, right? Complex numbers of this form behave exactly like real numbers g. You can add them and you can multiply them, and you just get back these real numbers. So we'll identify this g0 as the real number g. And in that sense, the real numbers are a subset of the complex numbers. We'll define, kind of conversely, we'll define j to be this 0, 1 number. If you square it on the previous page, multiplication, you get back negative 1, 0, which is pull the negative sign out and then associate that with the real number 1, you get back negative 1. And so we can really write alpha beta as, we can write it like this. That makes sense. And then you can work through, this is legitimate. It's beta 0 times 0, 1 will give me that. And so what we'll do is we'll write this as alpha, identify that as alpha, identify that as beta, and then call that j. So this number, we'll write it as alpha plus j beta with all those precise meanings in there, which is the usual way from now on that we'll write these things. We won't write them as ordered pairs anymore. Alpha is called the real part, and beta is called the imaginary part. So notice, it's not that j beta is called the imaginary part, beta is called the imaginary part. So the imaginary part of a complex number is real. It's the real number in front of the j. You check, that's how it's defined. Go into MATLAB, make up a complex number, and take the imag. You don't get back an imaginary number. You get back the thing in front of the imaginary part. So imaginary part is a real number. Just that can be a little source of confusion. The exponential function, if you're going to do this stuff, the sophisticated stuff, you've got to really work with the power series and so on. But since all we're doing is arithmetic, we can just define the exponential in terms of real exponentials. And this is what I got into last time. So I'm going to define if alpha and beta are real numbers, so this is a complex number, I'm simply going to define this exponential to be this. E to the alpha, that's the real part, and then the cosine and sine. And that's why somehow I'm going to simplify cosine and sine manipulations with complex numbers. So first of all, you can crank through e to this gamma 1, gamma 2, two complex numbers. We just break them up, then we follow the rules of multiplication, and we combine everything, and lo and behold, we get the e to the gamma 1 times e to the gamma 2 is e to the gamma 1 plus gamma 2, or I guess gamma 1 plus gamma 2. So the product rule for exponentials still holds. That's good. What if we have a complex valued function of a real variable? Exactly what I said. Complex valued functions of, say, time or something, but a real variable. So exactly what I wrote down. Complex valued function of a real variable. So that's really just two real valued functions, right? It's the alpha of t and the beta of t. And we can write it like that. Now, if I define the derivative, right, I'll just do the same thing. I'll advance in time a little bit. I'll look at the difference, and then I'll divide by epsilon and take the limit as epsilon goes to 0. You start writing these all out, right, and lo and behold, I'm going to take, it's really just going to be the derivative of the alpha function, because I'm going to get that divided by epsilon, and then it's going to be simply j times the derivative of the beta function. So the derivative of this complex number is, in fact, alpha prime plus j beta prime. Makes total sense. That's exactly what we mean by the derivative, though. Take the derivative of each component, the function of time. What is the derivative of the exponential? So now you can go through. We got the definition 2 slides ago of what the exponential was. We got the notion of what a derivative is, and you just do it. So e to the, or gamma is, there's our some complex number. I'll define gamma of t to be this time-dependent exponential. So if I break it out, of course, I get e to the alpha t, and then I get cosine beta t plus j sine beta t, and I broke it out completely. If I differentiate this, I'm going to differentiate this first, right? That's going to give me that. And then I'm going to do j, and I'm going to have the derivative of the other thing. Now I just start pulling things out and rearranging and doing some arithmetic. And if you check it out, you're exactly going to get this, right? I have alpha e to the alpha t cosine beta t, plus I have a j sine beta t right here. And then on the other ones, you get this other thing here. I pulled out a j, and that's why I had to flip a sign here. When I pulled a j out of this, I got another j. That -1 is really j squared. And this is exactly just, where did I lose myself? Alpha plus j beta, sorry. Alpha plus j beta times e to the alpha t cosine, which is exactly that complex number. So, and this is what I started last lecture, or ended last lecture with, just derivatives still work in exponentials. The derivative of this is exactly alpha plus j beta times that. This is just using our definition. What about thinking of complex numbers as phasors, right? So we can draw, in a two-dimensional plane, the alpha component and the beta component. We'll label this the real axis, because that first component is what we identified with real numbers. We'll label this the imaginary axis. And first we'll define the magnitude. So the magnitude of a complex number, or the absolute value of a complex number, is just the square root of alpha squared plus beta squared. It's real and imaginary parts. And of course, geometrically, that's the length of this phasor. So it is actually the length of the phasor. Once the phasor has a non-zero length, you can define an angle. The angle is defined as, pictorially it's this. Implicitly, it's the number such that the cosine of the angle is this component, right? This over the length, and the sine of the angle should be beta over the length. So it's kind of defined implicitly. You can kind of think of it as an arctangent. You have to be careful though that you don't, if I say the arctangent of 1/2, it could be up here, but I could also be 180 degrees over here. So you have to be careful with arctands because they aren't unique enough to get the angle totally right. So pictorially, magnitude and angle have natural interpretations if you represent the complex number as a phasor. What about the magnitude of the product of two complex numbers? So if I take the magnitude of the product, first I got to take the product, right? And then I'll square the magnitude later. So I take the product and I just crank through. That's the product right there. Now the square. Remember the magnitude said take the square of the real part plus the square of the imaginary part and square root it. So since I'm squaring it, I won't bother taking the square root. So there's the square of the real part. There's the square of the imaginary part. Now I'm going to do some manipulations here. I'm just multiplying that all out. I'm regrouping things. And when these are a bunch of chain of equalities, when I'm all said and done, I pull it apart and I do this. That's, of course, the square of the magnitude of the first complex number, which was alpha plus j beta. And this is the square of the magnitude of the second one. Take the square roots. So it tells me the magnitude of the product is the product of the magnitudes. Okay? Again, these are things you know, but I'm just reminding you where they're coming from. So that's important. Magnitude of the product of the magnitudes. What about the triangle inequality? So we can define complex conjugation. If you have a complex number, the complex conjugate is you flip the sign of the imaginary part, right? So it's, if you check it out, if you multiply the complex conjugate times the complex number, you get back the magnitude squared. That's the first thing you learn about when you're learning about complex numbers, how to divide by a complex number, right? Multiply the top and bottom by the complex conjugate of the denominator so that the denominator becomes a positive real number, right? So, and the magnitude of the complex conjugate is the same. What about if we add two complex numbers? Can we say anything about the magnitude of their sum? So I'll square it again just to work with that. So I know the magnitude squared is just a number times its complex conjugate. Complex conjugate moves through the summation. There's one step here that I have to do. These are easily chain of inequalities. Here all I'm doing is I'm saying the real part of a complex number is always less than or equal to the magnitude. That makes sense, right? The magnitude, the real part of alpha plus j beta, which is alpha, is certainly less than alpha squared plus beta squared, right? Which is the magnitude. This step's easy, right? For any real number, of course it's less than that. Because this is larger, the square root of that will be at least that large no matter what the sign of that is, and that makes it even larger. So that's the one step I'm doing there. This is smaller than this. You crank it through and I get these final things, take the square root, and I get what's called the triangle inequality. That the absolute value of the sum is always less than the sum of the absolute values. In a phasor diagram, that makes totally good sense. Here we just derived it using simple arithmetic. I think this is the last thing. This has some important formulas that we'll use today, though. So, for any real number theta, the complex number e to the j theta has magnitude 1. So, right, e to the j theta is just e to the 0 plus j theta. So e to the 0 and then cosine theta j sine theta. And of course, the magnitude of that is cosine squared plus sine squared, which is 1, no matter what theta is. So that is that's a complex number with magnitude 1. And its angle, if you draw it, of course, you realize its angle is theta. So this number is exactly the angle of that complex number. Okay. So that, I've kind of loaded the question by calling it theta, but e to the j anything is a complex number whose magnitude is 1 and whose angle is that real number anything that I said. You can take a complex number And I probably want to have this one, shouldn't be 0. It should say g not 0. So these aren't both 0. Here's what I can do. I can write it like that. Now let me pull out this square root. So when I pull out this square root, I have to put a square root here and a square root here, right? That's just an identity now. Now, this, of course, is the magnitude of g. And look at what alpha was the real part over alpha squared plus beta squared square root. That's clearly the cosine of the angle of g. And beta over the squared is clearly the sine of the angle of g. So therefore, you can write the interpretation of this magnitude and angle is I can write a complex number as its magnitude times the cosine of its angle plus j times the sine of its angle. But that's exactly just e to the j the angle, because that's exactly what we set up here, right? E to the j angle is a cosine sine. So a complex number can be written very succinctly as its magnitude times e to the j its angle. And again, that's a nice thing to, sometimes it might be useful to write it like that. And all I've done is just, by factoring that out and interpreting this term, that must be the cosine, that must be the sine, we get what we wanted. And this is the last slide, and this is a formula we'll definitely use today. So if I have a complex, now g is a complex number, and theta is an additional angle on top of that. So let's look at what is the angle of g e to the j theta. Well, we know what that, again, in high school you learned that's just rotating g, the complex number g, by an additional theta. So this must be the angle of g plus theta. Well, let's just verify, right? It's the angle of, I'm going to write g now as the magnitude of g times exponential of the angle of g. That's what we did from the previous slide. Now I do this. Now I can combine these into that summation. And so clearly the angle of this complex number, well, that's a positive real number. It's exactly that angle. So that's the angle. And so what that gives me is the real part of this. These are the important formulas that will end up again. The real part of this, let's just trace through it. So it's the real part of this, which is what we had right above. Okay, just that manipulation. So it's the real part of this. But we know what this is. This is a real number, and this gives me the cosine plus j times the sine. So the real part is the cosine part. So the real part of this is the magnitude of g times the cosine of the angle plus g, angle of g plus theta. Similarly, the imaginary part, at this point we're going to get the imaginary part, so we'll just pull out the sine, and we get sine, but it's the sine of this entire angle. Okay, so that's the quick recap of complex numbers. Any questions on that? These slides are posted. By all means, grab them. Okay, now let's go back to what I did last time. I'll go back to the thing. This is all in the handwritten notes or typed notes, but I'm going to do it at the board today. So let me remind you where we were. I'll just put down the last formula that I wrote down, and I wrote this out nicely today so I wouldn't get confused. So we have our normal differential equation. Okay, and we took a frequency, I'll call it, a real number, omega, and we had well, I want to now force the thing with the following forcing function. U of t is going to be e to the j omega t. So write cosine omega t plus j sine omega t. And I said that both a and w are not 0. Both a and omega not 0. If they were, I didn't put this up, but let's just do it. If they were, then we'd really be talking about the following equation. X dot equals, it's a 0, that's gone. And if omega is 0, this is just a 1. So we'll really be doing this differential equation, right? And I know the solution to that. The solution to that, I don't know, it's just b times t plus x0. So if they're both 0, this is trivial. That's the solution. It's just something that goes up. I'm not interested in that case. I'm interested in the case where they're not both 0. And then what we derived was this. We derived that x of t was e to the at, x0, and I want to get the signs right, minus b over j omega minus a, plus, and then it's just b over j omega minus a e to the j omega t. Okay, so that's what we got the solution to be. So then, regardless of whether A is positive or negative, regardless if things are blowing up or not, now we specialize to, let's say, the case where A is less than 0. So then we know that this is decaying, right? That implies this is decaying. And this is just some constant complex number. So how quickly is it decaying? Well, it's decaying with the time constant, right? After, if the time constant is -1/A, after 3 or 4 time constants, this will be 1 or 2 or 3% of what it originally was. Regardless of how big it is, it'll be crushed down by, a factor of 100. So this is decaying with its time constant, right? Time constant equal to -1/A. And what remains is this kind of steady, complex sinusoid that just has a different magnitude. So this is this remains, right? So what it tells me is that as t goes to infinity, right, x of t starts to look like this. Maybe I'll make it with an arrow. X of t goes to, right, b over j omega minus a e to the j omega t, right? Because whatever, the other part is just decaying. So let's call this the steady state behavior of x. Of that function x, right? That's what it's looking like. So what we got, it's very similar but more general than what we did before. Here we got, if we put in this type of a function, eventually, and this is how quick it happens, x starts to look like this function. Right? This forcing function will ultimately produce this response. Everybody get that? What if we do omega equals 0? Let me tell you, we've already done this before. So if I do omega equals 0, what is that? That would have been really, u would have been equal to 1. U of t was 1. And then what we got is x of t is, because right, if I put in omega equals 0, this is 1. And x of t is going, let me substitute omega 0. Omega 0, that's gone. I'm just getting negative b over a times 1. So this is just generalizes the constant input that we already knew how to do. Right? It's a constant input. So there was what we call the steady state gain. So what I'm going to now call this, from u to x. So somehow I should call this also a steady state gain. I should call this is the sinusoidal steady state gain, we'll call it. Maybe at frequency omega. Okay. Because if you put in a sine wave, a complex sine wave, you get out a complex sine wave, exactly the same complex sine wave, but amplified or attenuated by that fixed number. This has nothing to do with the input. I mean, it's frequency dependent, but other than that, it has nothing. There's no time dependence in that. That's just a number. Does everybody understand that? If I were calling it that? So that's cool. So now, of course, if I had replaced u, suppose I had done this. I had done u of t was not 1 times e to the j omega t, but suppose I had a constant amplitude. So suppose u bar was just some fixed complex number. Like maybe just 2 e to the j omega t, or -6 e to the j omega t, or some complex number. Well, then if you go through all the integrals, right, the only thing that's going to happen is, what's going to happen is I'm going to get a u bar right there, and I'm going to get a u bar right there. Right? Everywhere there's a b, there must also be a u bar, because it was also there as well. So I can rewrite this. I'll take the time to rewrite that. Then this is going to, of course, cause x of t to be e to the at x0 minus b u bar over j omega minus a plus, and I'll write this one just a little different. I'll write it b over j omega minus a times u bar e to the j omega t. Again, in the case of a stable system, this is dying away, so x is simply heading towards this. And again, it looks like a gain, right? If that was the input, what we get out is that, but scaled by this number again. Yeah?
I just wanted to clarify, the first term in x of t is what's causing the decay, and then the second term is what's causing the oscillation?
Yeah, this is decaying, or it's blowing up. If it's blowing up, you won't really be able to see this, because it'll be a small sine wave superimposed on something that's blowing up. But if this is decaying, this is what you'll eventually see. It's always there. It's just if it's blowing up, you kind of can't tell that it's there, right? Okay. But yeah, this is some sort of complex sine and cosine omega t, right? That's what we saw. And then it's got some different amplitude. All right. Yeah.
Is that a complex number?
Everything's a complex number here.
I mean the b over.
Yeah, this is a complex. Even if a and b are real numbers, that's complex, right? So this is a complex number.
How do you bring up the real number?
No, so now we got to interpret it. We're not ever going to be able to put a complex sine wave into our system, right? We can maybe put a sine wave in, or we can put a cosine wave. This was this abstract mathematical kind of just construct. Let's put a complex sine wave in. The reason why I did it is because, remember why I did it? Because when I had to do this integral, if I put e to the j omega tau here, that combines with this really easily. It was very easy to do the antiderivative. And if I put a sine of omega tau here, I mean, it's still not hard, but obviously it's a different type of integral. I got e and sine. I got to do the integration by parts, and it's messy. I want to get a nice interpretation of this where the messiness is left to some other, to doing something else. There's still, it's all there. It's exactly the same, but we want to do it like this to make it easy. So I did this abstract thing, put a complex sine wave in. We got this really easy answer. There's some decaying part if it's stable, and then just you get out the same sine wave, but it's got a different amplitude in the sense of a complex number. This is a complex number. It depends on frequency. Let's do one more thing, and then we'll do some plots, or then we'll try to interpret this, I guess. Yeah.
So you said that if the first part decays, you're just going to put that second part of the.
Yeah, because this is an exponential, right? This is a real exponential just doing that if it's decaying. Okay. Now this thing is made up of. We know that this term is made up of cosine omega t plus j sine omega t. So this thing doesn't go away. This just keeps persisting, and it's some sort of oscillation in the complex space, right? But it's exactly at the same frequency that we put in. We put in some function like that in a complex sense, and we got out a function. So if you ignore this thing, which is going to decay after after a certain amount of time, it's like you put in a sine wave and you get out a sine wave. And you put it in at frequency 2, it comes out exactly at frequency 2. Now how big it is relative to what went in is determined by this factor, right? That make sense?
Yeah.
Okay. So let's first of all just add an output equation. So we haven't messed with the output equation too much, but remember output equations there's not much going on in them. I'm just going to say Cx plus du. Right, the differential equation was above. Now I'm just going to say, what if y isn't just x, right? For example, we could have it just be 1 times x plus 0 times u. Then y would just be equal to x, but I could make it other things if I wanted to. The variable I care about could be some combination of those. So if I do that, all I have to do is multiply this times c, right? So I just have to put I won't do this to you because I just put a c there and a c there, and then I just have to add d times this on top of the whole thing, right? Now I'll do this in one step, but I will rewrite it for you. So if I do that, what y becomes very simple. It's easy to derive this. I mean, it's easy to just check it. You'll be able to see it, right? Visually. So then y becomes c e to the at x0 minus b u bar over j omega minus a. We don't really. I'm writing this out, but usually we're not going to even care about what that term is. Plus cb over j omega minus a plus d times u bar e to the j omega t. Right? That's what y would become. Does everybody agree that all I did was tack on the du and the c times x? So again, if a is less than 0, then this is decaying. And this is what we're left with. This is what y approaches. This is the steady state behavior of y. Now again, you can get back, just by setting c equal to 1 and d equal to 0, you get back to what we had for x. X is just a special case of y. Y is general. It's some combination of x and u. X is a one particular combination. So this is just going to completely encompass everything we just did. So what am I going to call? Now remember, what was this? This was due to what input? Due to u of t equal u bar e to the j omega t. So what am I going to call this box? Anybody? I'm going to call that what? The sinusoidal steady state gain from what to what? From u to y. Right? So the box CB over j omega minus a plus d is going to be the sinusoidal steady state gain, right? I guess at frequency omega from u to y, right? That's just terminology. But the terminology makes sense. It makes sense to call it that because that's exactly what it is. It says if you put in a sine wave in this complex sense, you just get out a sine wave amplified by that number. Let me just get ahead of myself a little bit. When we go to systems that have more than one differential equation, all these things are going to be matrices. A is going to be a matrix, B is going to be a matrix, C is going to be a matrix, D is going to be a matrix. When we get there, I'm going to define it, I'll derive it, but you know what it's going to end up being? It's going to end up being this. That's going to be the sinusoidal steady state gain when everything is a matrix. And look, it's just the divide by j omega minus a is going to involve the inverse of j omega times the identity matrix minus a. That's the matrix generalization of this. The c and b are going to be on opposite sides and the plus d. So you're going to see this formula like 4 weeks from now. The whole goal of the way I'm laying out the lecture is I want to do 4 weeks of only one differential equation. And we're going to study control. Starting next week, we'll analyze the control systems we've played with the math we're doing now. And we'll go over all the issues that come up in a control system, but the math will be extraordinarily simple because we won't be doing anything more complicated than a first order differential equation. Once we have that in place, and you all kind of understand what the point of the course is completely, then the last 10 weeks we're just going to go to more than one differential equation. And we're going to just redo everything again. It'll get more nuanced because once we allow more differential equations, it's going to open up a few more possibilities of things that can happen. But there won't be any new questions being asked. All the questions will be the same questions we asked and answered, and we'll figure out how to ask them and answer them as we go on. So that'll be, starting, hopefully 9 or 10 days from now, we'll do that. So every formula I'm deriving, later on you're going to go, oh, I see, that was just a scalar version of something that we're doing now in more generally. And it should fit together nicely. So anyway, so that's that. So now I think the question becomes, okay, someone said, how does this relate to putting in a real sine or a cosine? What we really can do. So let's do that. Let's think about it. What we solved was the following problem. We just solved. We forced the following. We'll only worry about the x equation for a second, and then we'll come back and realize that y doesn't change in what I'm about to say. So we basically looked at this equation. Right? That was the input, u of t. This was u of t. And this is complex, right? So, but if you think about it, I'm going to take the case. We're going to always consider our systems, the systems are going to have real coefficients in them, right? Everything's really real. We're just playing math to deal with sines and cosines. So our system parameters are real, right? So we know though this complex input produces a complex response. So let's just break it down. Let's be more general. We'll break our U input into a real input plus J times the imaginary part of the input. Now we know that's going to cause a solution that's going to be generally complex. Its real part plus J times the imaginary part, right? And maybe the solution maybe we started at some real initial condition plus, a complex initial condition that consisted of a real part and an imaginary part. So I guess I should have, these two things together, the input and the initial condition produced that. Now, since the A and B are real, question, since A and B are real, what is actually causing the response XR? Does the imaginary part of the forcing have any influence on the real part of the response? Does the imaginary part of the initial condition have any influence on the real part of the response? And vice versa. Does the real part of the initial condition have any influence on the imaginary part of the response? Does the real part of the forcing have anything on that? And the answer is no. Let's see why. Let's write down what the differential equation is. The differential equation says x dot. But we know the derivative of this is just the derivative of that plus J times the derivative of that. So I know the differential equation is just XR dot plus JXI dot, right, equals A times XR plus JXI plus B times UR plus JUI. Now, what's really important for me to say the real and imaginary parts don't get mixed up. What's going to be critical is that A and B are both real, right? If A was a complex number, then of course the real part of X is going to multiply the imaginary part of A and create some sort of imaginary part. But this is real. This is real, and this is real. So therefore, if I now just break up both sides into their real and imaginary parts, if I simply break this up into the real and imaginary parts, there's no mixing involved, right? And I'm simply going to get XR dot, I'm not going to write the time, is AXR plus BUR, and I'm also going to get XI dot is AXI plus BUI. Right? They're totally separate. So the real, when you abstractly think about forcing something with a complex valued input, the real part of the input is what's causing the real part of the response, and the imaginary part of the input is what's causing the imaginary part of the response. And they're both governed by exactly the same differential equation. Okay? So, you're going to tell me exactly what's going on. So, let's call this. Okay, the same thing's happening with the output. I should have said that, right? Y is Cx plus du. But this has got a real and imaginary part. That's got a real and imaginary part. But this is real, and that's real. So therefore, the real part of y is only dependent on the real part of x and the real part of u. The imaginary part of y is only dependent on the, I'll write it down. The real part of y is c times the real part of x plus d times the real part of u, and the imaginary part of y is c times the imaginary part of x plus d times the imaginary part of this. So again, the real and imaginary parts are just evolving separately by exactly the same differential equation and output equation. Okay, with that in mind, let's also call this function of frequency. I'm going to call that generically g of omega. It obviously depends on the parameters a, b, c, and d, but let's think of those as like somehow fixed, and we all know what a, b, and c, d we're talking about. So I'm bookkeeping the dependence on frequency here. So that'll be, and we'll call that the frequency response function. Frequency response function. F RF. Okay? I hope that's not an acronym that I don't know, but, or an abbreviation. If it is, you can email me. Okay? So, that's what we got, right? So what we learned was the following. Here's what we did 2 or 3 boards ago. We said, for instance, if u, let me make, let's just, okay, so if u is equal to e to the j omega t, and the system is stable, then we got that y of t will go to, right, it will approach g of omega times e to the j omega t, right? There's some exponentially decaying things, but that's what will happen. That's a quickly way to summarize what I had before, because I've just, where I wrote down a formula, I've just now written down that thing. Okay, so now, but this of course is really just the cosine of omega t plus j times the sine of omega t, right? That's what the top thing is. And this is just equal to, now I'm not going to do anything, but I'm just going to write, this is just equal to the real part of g of omega e to the j omega t plus j times the imaginary part of g of omega e to the j omega t. Right? I haven't done anything, I just said a complex number is its real part plus j times its imaginary part, right? But what did we just derive up here? The real part of the forcing function is causing which part of the response? This forcing function is precisely what's causing this, and this forcing function is precisely what's causing this. Right? So now I know if I put a cosine omega t in, actually I'll put a sine, yeah, I'll do a sine. If I put a sine omega t into this A, B, C, D system, what I'm going to get out as what I'll get out, so this is my u, and that will lead to a y that is itself, it's got a little transient, but it's approaching just this imaginary part, right? The imaginary part of g of omega sine of omega t. But the last slide that I had said it was this type, sorry, not sine omega t, what am I doing? E to the j omega t. Let me remind you what the last slide said. The imaginary part of g e to the j theta is equal to the magnitude of g times the sine of theta plus the angle of g. That was the last slide, one of the identities we got. So now I can write this pretty cool. I can write this as, this is going to be equal to the magnitude of g times the sine of omega t plus the angle of g. Okay? We had that, this is another, if you want to tattoo anything, this is something to tattoo, right? So now, end to end, I got exactly what I want. If I put in a sine wave, and the system is stable, then I'm going to get out a sine wave in the output. There'll be that decaying part, but that's decaying as fast as the time constant. So what's going to come out, it's going to be a sine wave. It's going to be exactly at the same frequency. It's going to be shifted, though. It may be, you can think of it as a little ahead or a little behind. It's not going to be aligned because of the angle of g. And it's not going to have the same magnitude. If I put in magnitude 1, it's going to have a different magnitude, whatever this is. So this frequency response function, as a complex number, its magnitude determines the amplification or attenuation, and its angle determines the phase shift. But we now know exactly what happens when you put a sine wave in. And if I had put in the cosine wave, well, then it would have said cosine is producing the real part, but that would have been the magnitude of g times the cosine of omega t plus the angle. So, it's easy to do, right? The real part of this was g times the cosine of theta plus the angle of g. So you don't get anything different for putting in a cosine wave, as you'd expect. You get exactly the same thing. Cosine produces magnitude of g cosine of omega t plus the angle. Yeah. Anything?
So how do you take the magnitude?
Oh, so now we gotta, if I give you data, you gotta take the magnitude of that complex number. And you gotta take the angle of it, but it is something. It's a number, right? So remember, the magnitude of a complex number, the magnitude of this is alpha squared plus beta squared. Now this isn't written in real plus imaginary form. You'd have to convert it to its real part and imaginary part, then you'd get it. And the angle, of course, is the it's the arc tangent, 2 coordinate of beta alpha, right? In MATLAB speak, you put in the imaginary part and the real part, and it tells you what the angle is. Let's do some examples though. Let me fire up the thing. So I got a little MATLAB file here. This is all posted. So let me show you what I did. Well, actually, let me just publish it and let's just scroll through it. Okay. So I've got oops, sorry. So I'm going to pick. Where's my pointer? I'm going to pick a vector of frequencies. I'm going to plot it for all frequencies. I'm really going to plot it for, I guess, 10,000 frequencies from 0 to 10. I'm going to pick out 2 specific frequencies. I picked out 1 and 5. So sine of t and sine of 5t. And I'm also going to, so I'm going to plot this frequency response function, but I'm also going to do the simulation. I'm also going to force it with a sine wave and see what happens. So I'm making up a time vector going for, so many seconds, 2 periods of this slow thing, 2 full periods. I'm making up a time vector, and I'm making up a forcing function, which is the sine of omega 1 times t and the sine of omega 5 times t. So, okay, that's fine. Then I'm just going to take a system. So here's the system I made up. It's stable, and then I've got b equal 1, c equal 1, d equals 0. Then I'm going to form g. So g is, remember, it was d plus c times b over j omega minus a. And I'm doing an element by element divide there, because this is the whole vector of frequencies. So this is my vector of my frequency response function. This is exactly what I want to plot. So, and then I can do it, then I'm also going to grab it just at this particular frequency and that particular frequency. Those are just 2 points. And now what I'm going to do is I'm going to plot the frequency response. I'm going to plot its magnitude on one plot, its angle on another plot, and I'll plot these 2 dots on there as well. So when I do that, right, that's what we get on the left. Let's see. So there's the magnitude as a function of frequency. It starts at 1, and in this case it just drops off. As frequency increases, the magnitude drops off. There is what it is right at frequency 1, and there's what it is at frequency 5. The angle turns out to be negative number. So this thing, it's as a complex number, it's going down, into the 4th quadrant, which is where negative angles are. And the angle in radians just happens to be this and this. Now what I'm going to do is I'm going to put in a sine wave. So now I'm doing a time response. We'll scroll back. I know you've got to give me 2 extra minutes. It's Friday. That doesn't make any sense, but well, you got Saturday and Sunday off. So what I'm doing is I'm just making up. See, I'm just going to use OD45. I told you I'm not going to make you do too much, by hand things. So I'm going to make up my function handle. My x dot equals ax plus bu, right? So x dot is a times x plus b times the value of u. I'm just going to use the interp function. I had a grid of times and a grid of values, and so at any time t, I should call interp. That gives me u at that time t. So this is the function handle that'll solve that differential equation. I'll solve it, and I'll plot it. So what I'm plotting here is the response. The forcing function is red, and the response is blue dashed, or black dashed, and this is at frequency 1. So it says, first of all, the magnitude of what comes out should be about 0.7. And although this legend is hiding it, you see the magnitude is about 0.7. I put in something of size 1, and eventually I'm getting out something of size 0.7. You see at the beginning it doesn't look like a sine wave, right? You can see there's a little bit of something else going on. That's that transient that has to die away. But after 3 time constants, this is 0 to 10 seconds, I think. And so the time constant A was -1, time constant is 1. So after 3 time constants, the black one looks pretty much like a sine wave. What about how far is it behind? Last thing, and then I'll let you look at everything else. So the angle here, look at this. The angle is about -0.8. And in your homework, which you're working on now, we saw that when we write omega t plus phi, it really says what you want to look at is phi over 2 pi. That's kind of the fraction of the period that you'll be ahead or behind, depending on the signs. So 0.8, what is 0.8 over 2 pi? Okay, this is 6. So it's about, I don't know, what is that? I'm just having a 1/8, roughly 1/8, right? So this thing should be about 1/8 of a period. Now this is negative, so if you go through it, it's 1/8 of a period behind. Behind meaning it actually happens later, because it's behind, right? So on the graph it looks like it's ahead, but ahead is later in time, so it's actually happening later in time, which means it's behind. So let's just check that it's exactly 1/8 of a period. Where's my pointer? So look at this. Look at the period is here. It's from this red to red. And this is how far it is behind. The black is a little bit behind, and lo and behold, it's about 1/8 of a period behind, which is exactly what I saw. Now I go to the higher frequency. We'll quick do this as long as you're sitting there. Okay, -1.4. The magnitude should be much smaller, and there it is. It's much smaller, right around 0.2. So it's been attenuated. And how far behind should it be? Well, this is about pi over 2. So pi over 2 divided by 2 pi is about 1/4 of a period, right? So it should be about 1/4 of a period behind, and that's exactly what the black one is. It's hard to see because the scales are so different. By lining them up magnitude-wise, you see that the black one is about 1/4 of a period behind. So this frequency response function tells you what it does to sine waves in the steady state, magnitude and phase shift. And right now, we're just going to plot them. We'll learn how to plot these frequency response functions pretty accurately by learning, what's called Bode plots. We'll learn how to do this by hand. But you're going to do them with the computer. All right? Have a good weekend. I will post them.